form, this would be pulley, no yawning. All yawns must stop now. The next person to yawn, some hopefully obvious things, but clear. I have a mount that holds the pulley, so that's what the green box is. That was the thing that's holding the pulley in place. And there's a string on the outside edge of the pulley. Say right there. And the string is connected to a box. Like that. And because I think this is not an unreasonable thing to do, we're going to assign some masses to this. Instead of doing M's and R's, which I think has been pretty contrived all this time, let's say that the pulley has a mass of 2 kilograms and a radius of 20 centimeters. That's the pulley. And let's say that the box has a mass of, let's go with 2 kilograms too. Now, I want you to figure out what the acceleration of the box is. But I realized from my last class period that might be a bridge too far for you too. So here's what we'll start with. Can you set up and what the net force and net torque is for each object here? And I asked that because I got weird questions in the last class period. So try and just set up the net force and net torque. If you don't know where to begin, and I know some of you are going to say you don't know where to begin, and you ask me that every single time, when I just say you're going to do a net force, net torque problem, it starts with a free body diagram. You draw arrows. That's where it always starts. And you ask yourself, is there weight acting? Is there a normal force? Is there tension? It just start there. Okay, I gave you guys a few minutes, and you guys have a start. I'm going to ask questions, and I could just like single you guys out and try and embarrass you in front of the group, but that's really not been my MO ever. But I do like the idea of you guys being the ones to answer here. So, do you want to start with the block or the pulley? Block. All right. Does a block experiencing any unbalanced force? Yes. Okay. How many forces is the block experiencing? 2. Can you name the 2 forces acting on the block? All right, so 20 newtons of weight. And what else? Tension, which is an unknown amount but is less than 20. Would you agree with that statement? All right. Now, some people are putting like TR and TL. I mean, there's only one tension, isn't there? So I'm just going to put T. I don't have another box. All right. Is the box experiencing an unbalanced torque? Is the box going to spin? No. It might after it hits the ground, but for the way we are setting the problem up now, is the box spin a part of the problem? Okay, that was a problem last class period, which is why I'm bringing it up. So I think we're done with the box when it comes to drawing the arrows, but we do have to we do have to write out an expression that matches what's happening with the arrows. So that's us starting with is it net force equals 0 or MA? I'll put 2A because the box has a mass of 2. So you have to make a decision here about whether downwards is going to be positive or upwards is going to be positive. All right, so can you write out the rest of this expression? This is where we start every time.
Wait for to try to find I?
No, I'm just talking about the box. I is for things that are rotating. So I just want you to take and figure out what this looks like. Basically, what is this part? So we got it? Does it look like this? Is this what you put? Now, if you have to draw some arrows on the pulley. How many arrows are you going to draw? Is the pulley experiencing a gravitational force? It is. So I think we have a gravitational force. So let's draw an arrow for that. That'll be mg, or 20 newtons, because it's got a mass of 2. Is there anything touching the pulley that can be applying a force? Name something. The what? The thing that's holding it, sure. I don't really know what kind of force that is. I'm going to say it's a normal force. It could be a tension too, I don't know. But it's definitely holding it in place. It's whatever that thing is doing to the pulley there. Is there anything else touching the pulley? What? The rope, the string, sure. So the rope string thing. So yes. This is a Newton's third law pair. The box doesn't touch the pulley directly. The box it touches the string, and the string touches the pulley. So that internal force is considered a third law pair. They are the same size. All right, now here's a hard question-ish. What is the net force on the pulley? 0. Did the pulley go anywhere? So net force on the pulley is 0. Quite literally, n minus 20 minus t equals 0. I don't know that we need this. We weren't asked questions about where the pulley went. But that's still true. I'm bringing it up because there are 3 forces acting on the pulley. We often forget that, but the pulley stays in place. For the same reason the box didn't spin, because there was no torque acting on the box, there's no net force on the pulley, so the pulley didn't go anywhere. But the pulley spun, didn't it? So there is an unbalanced torque. Because we believe the pulley spins, you do have to identify the pivot point in the problem. Where did the pulley pivot? The middle, sure. The pivot point for the pulley is the middle. So of the 3 forces that act on the pulley, which ones cause a torque? Does the normal force cause a torque? Why? Why doesn't the normal force cause a torque? Yes.
Because the force has been applied right on its pivot point, so it has no can't be affected.
That's it, right there. That's the perfect answer. That force is being applied at the pivot, so it can't affect the torque. We need something that's not applied at the pivot point. Is there any force applied away from the pivot point? Tension. How far away is the tension applied from the pivot point? So I'm going to put 0.2 meters. Do that to convert to meters. All righty, so we do have an unbalanced torque acting on our pulley. So I get that this is a more complicated thing. Torque requires more consideration. So it's not just the mass, it's the moment of inertia, and it's not just the acceleration, it's the angular acceleration. And torque isn't just a force, it's a force and where it's applied and in what direction. There's a lot more to consider. That's why this is harder, but that's okay. Just because it's harder doesn't mean it's impossible for you. I say we probably handle the torque part first, shall we? So we want to figure out how big is this torque. Torque has 3 parts. So what is the torque arm length? 0.2. What is the thing causing the force? Unknown tension. What is the angle at which the tension acts relative to the torque arm? 90. So sine of 90 degrees. Excellent. So that is our torque. I'm going to reduce it down to be 0.2 times t. The moment of inertia is based on the shape of the object. What shape is this? It's a disk. Do we have in our heads the moment of inertia of a disk? So, all right, there we go. 1/2 mr squared. You have all the numbers there. Work it out. 1/2 times 2 times 0.2 squared. So 1/2 times 2 times 0.2 squared. Ooh, I don't think it's 0.2. Yeah, 0.04 then. The units are kilograms meters squared. All good? Alrighty, so we're going to replace I with 0.04. All right, alpha. We've been doing stuff with alpha, right? In fact, that was the whole thing about yesterday is the alpha was kind of weird because we had the possibility of two different accelerations. The box on the big side would accelerate one way and the box on the inside would accelerate another way. You have to ask yourself when you reach this moment and you're trying to figure out what to do with the acceleration, is there a way to replace the angular acceleration with the linear acceleration of the box? That's a hard question and can be confusing. You're trying to figure out if this is true for your problem. One way to answer this question is to consider the following idea. If the pulley spins one time, will the box fall one circumference? Okay, so if that happens, if you know that that happens, then this is true. If you don't know if that happens, then you might have to think more about it. Yesterday we saw a situation in which the spinning of the pulley created two different accelerations. One for the box on the outside radius and one for the box on the inside radius. And they weren't the same because there's two different radii. Is that the case in this problem? No. So in this problem, we have a pretty straightforward. We can set our angular acceleration to A over R. Okay. I think that's the rest of this is going to be arithmetic and algebra. Right? You notice that we have two equations and two unknowns. Do you see it? There's one over here and one over here. Two equations and two unknowns. They both have t and they both have a. I don't know if you can do this or not because there's numbers here. So I would encourage you to take a few minutes and do the arithmetic, and then we'll come back together. So 2 minutes, I think, is what I want to give here. I got stuck, and I know where. This side you're probably fine. Did you get 0.2 t equals 0.2 a? You know that if you want to be able to add these two things together, this has to be just t. So you have to divide both sides by 0.2. So yeah, t equals a. Yeah. So I know that looks weird because how does tension equal acceleration? It's because the mass there ends up being 1 kilogram. If you look back at the old way we would have done it, the r's would have canceled out, and we would have had 1/2 m there. And the mass is 2. That's the only thing. There's a 1 kilogram in there somewhere. It's just that we didn't write the 1 there. We add these together, though, we get 20 equals 3a, or a equals 6.7 meters per second squared. I don't know if this is something you could do by yourself or not. I'm afraid probably that some of you would have struggled. Yes?
Why didn't we add the n minus 20 minus t into the equation?
I'm sorry.
Why do we do?
All right, how many arrows did you draw? 2. Tell me one. Tension. Where'd you draw it? Somebody, when I was walking around, drew an arrow like this last class period. I don't think that's where the force is applied. Do you? No. A little more to the left. Yes, I agree. Is there any other force acting on the toilet paper? The weight. Where would I draw that? Excellent. From the center. 2 forces acting on the toilet paper roll, or disc. All right. Did our toilet paper roll accelerate? So it changed location? Okay. So that means the net force isn't 0. So net force equals ma. Can you flesh that out for me? Finish it off. What should it look like? Okay. mg minus t equals what? ma. Okay. Yeah, I am not trying to trick you. mg's downwards. T is upwards. We picked downwards to be positive. Seems reasonable. And it accelerates downwards. All perfectly plausible. Did the toilet paper roll spin? Okay, so net torque does not equal 0. Net torque equals I alpha. All right, now this part's tough, kind of. Not really tough, but it's tough because you may not understand it. So it spun. Where's the pivot point? In this room, there are probably 2 opinions on this. So where do you think it is? What's that? Right where the tension is? I bet there's another person in the room who thinks something different. Could it be at the center too? That's right. Which one of these is the actual pivot point for the problem? You can choose between the 2. And here's why, actually. And in fact, we're going to do both problems because in 6th period, there were stronger feelings about which one was the right one. So I wanted to prove to them that it doesn't matter. But here's why it doesn't matter in this problem. This is important because sometimes it matters and sometimes it doesn't. It seems like that feels, like I said earlier, like haphazard. It's not. It has to do with something called reference frame. Believe it or not, us in the room, as we observe it, the actual toilet paper is pivoting about this location for us observing it because I'm holding this point still. So that's where it's pivoting. The thing is that it unrolls and then there's a new point right below that one. And that becomes the next point that's pivoting because it's unrolling. That's the whole nature of rolling, is that the pivot point's always changing, the point that is not moving with respect to the object. So that's what's happening. However, if you could shrink yourself down small enough and ride along with the toilet paper, like if you got yourself into the hole of the toilet paper, from your vantage point, everything is spinning around you because you're falling with the toilet paper. So from the vantage point of the toilet paper, this is the pivot point. It just depends on which vantage point, because both of those are reference frames that are acceptable to observe the problem. So we're going to do the problem both ways. I will let you choose whether we do way 1 first or way 2 first. Do one first, done. Okay, that is all true. All right, so we're going to do our pivot point there. How many forces cause a torque in this problem if we choose that as our pivot point? Only one. So what is the distance from our pivot point to our unbalanced force? R. So let's start building our torque. Our torque is going to be R times, what's the size of the force? mg. And what is the angle between the torque arm and the force? Excellent. So that looks like our unbalanced torque. Okay, you're not going to like this part. Although that is perfectly acceptable. Our next job is to figure out the moment of inertia. And this is a disk. But we're not rotating it about its center. We're rotating it about its edge. So you made a choice. We're going to stick with it. But this choice requires that we get a new moment of inertia. Now, look, I want to be very clear. There are always going to be advantages and disadvantages to these choices. If we had made the other choice, there's a disadvantage to that one too. So the disadvantage in this choice is we have to deal with the moment of inertia. This requires use of something we talked about last week, but you won't remember it. That's why I have to bring it back up. It's called the parallel axis theorem. That's when you shift the moment of inertia from the center of mass to another axis. So we're shifting it from here to here. And if you don't remember what it is, it's I, center of mass, plus mx squared, where this is the shift. So let's do this part. This is still a disk, so I, center of mass, is still going to be 1/2 mr squared. But now we have to add the portion that shifts the moment of inertia. M is just the mass of the object. That's easy. How far did we shift it? R. So r squared. Okay, that's it. That's how much work it is to use the parallel axis theorem. Is that a lot? No, it's not. Don't say yes. It's a wee little bit of work. And here, I'll let you do this part. What's 1 plus 1/2?
1/2. Wait, no, 1/1.
It is 1 and 1/2, or you could say 3/2. Either of those will be fine. I'm going to say 3/2. All right, so we did the heavy lifting. We did the hard part. Okay, we had to use the parallel axis theorem. It's terrible. It was, I know. So now we can put everything together, though, because we have our torque, we have our moment of inertia, and this one, A equals alpha times R by definition, because it is rolling. Anytime something is rolling, you can automatically use that. You don't have to worry about it or anything. So here we go. Let's put all the pieces together. R mg equals 3/2 mr squared times A over R. All the pieces together. Is it clear to you all the R's cancel here? I think so. Is it also clear that the M's cancel? So all the R's go away and the M's go away, and I'm left with G equals 3/2 A. Yes.
How do the R's go away if the one next to the M is squared?
Okay, so this R cancels with the one that's squared. That leaves an R on this side and an R on this side. So those two go away too.
Oh, okay.
That okay? Yeah. All right. So going back to where we were, that'll mean G equals 3/2 A. So you're going to love this. A equals 2/3 G. 6.7. All right. So this one had the advantage that we never had to use this. Did you notice? We got our answer from a single relationship. That was the advantage of using this pivot point. The disadvantage, we had to use the parallel axis theorem. So every choice like this is going to bring advantages and disadvantages. But I said we would do it both ways, so we're going to do it the other way in the next 4 minutes. So you guys who are writing stuff down, I'm about to erase all that. Are you good?
Wait, so is the answer A equals 2 divided by 3 times G, or is it G equals 3 divided by 2?
Well, the answer was the acceleration, so that one. Okay.
Because he times it to the other side and it flips each way.
Exactly. All right, guys. We're going to switch, and we got to do this hastily. But there's less to do here. First, our pivot point's now at the center, so does the weight cause a torque? No. What does cause a torque? Tension. So how far away is the tension from the pivot point? R. So can we say that our torque is R times T times the sine of 90? Excellent. That has to equal the moment of inertia. This is just a disk. We don't do any shifting here. So it's just what? 1/2 mr squared. And is this still unrolling? So A over R. Let's simplify it by getting that sign out of the way. RT equals 1/2 mr squared times A over R. Do we notice that all of the R's cancel this time? I noticed it too. The M doesn't cancel this time, but all the R's cancel this time, just like before. So T equals 1/2 MA. Here's the downside of using this one. This isn't the answer, right? It doesn't give us the answer directly. So now we're stuck looking for the answer, but like our other examples, we can take this and write it over here. So although this one, we don't have to worry about the parallel axis theorem, we do have to use both equations because we got tension in it. But does this one look like it adds together pretty quickly? I think so. Do the T's cancel? So the left side will be mg. 1/2 MA plus MA, what does that equal? 3/2 MA. Looks like I can cancel out them M's. Don't you see it? Excellent. Multiply both sides by 2/3. I'm sorry, by 2/3. So A equals 2/3 G, or 6.7. But again, same answer. You can do it either way. Anytime something is rolling, you can choose either location to be your pivot point. All right.